Hi, in this video we will talk about ridge regression, which is a regression method that offers a way to estimate the coefficients of the linear regression model. It introduces a little bit bias compared to the least squares method, but can reduce the variance significantly. And unlike the least squares method, it can also be used when there are more unknown parameters than data points. Just a reminder, we consider a linear regression model here, and we would like to estimate the unknown parameters beta 0 and to beta p from the data y. And a classical way to do this, to estimate the coefficients, is to use the least squares method, that is, to minimize the residual sum of squares. Now, the ridge regression estimator can be found by minimizing the residual sum of squares plus a quadratic regression term. And here, lambda acts as a tuning parameter, and the penalty term is small if the parameters are small. So this shrinks the coefficient closer to 0. And notice that we do not want to shrink the intercept beta 0, which is related to the mean of the response y. And if lambda is 0, we get the least squares fits. On the other hand, if lambda goes to infinity, then the coefficients tend to 0 and we get the 0 model. And somewhere between the two extremes is an intermediate value of lambda that minimizes the mean squared error. We can write the minimization problem using matrix notations, and here we have assumed that the lambda 0 is 0 to simplify the notations. You can also achieve this by standardizing the coefficient. The minimization problem is quadratic, and it actually has an analytic solution. And notice that the x transpose x is not necessarily invertible, but adding the lambda plus identity operator makes the inversion well defined for any lambda greater than 0. So let's next consider an example where we want to predict credit card debt using credit card data from 400 people. There are 10 predictors, but only 4 of them have relatively large coefficients. And we fit the model using ridge regression. And in the picture, you can see how the estimates for the coefficient change with different values of lambda. We start with the lambda 0, which corresponds to the least square solution, and when the lambda grows, the coefficients shrink towards the 0, and this is also why these methods are sometimes called shrinkage methods. Even though the coefficients generally shrink when the lambda grows, some of them can also grow momentarily. And it is important to notice that even though the coefficients tend to 0, none of them are set to exactly 0. Now, on the previous image, we saw how the estimates of the parameters, so the betas, change depending on the lambda. But why would a model found using the ridge regression do better than one attained using least squares? The answer here follows from the bias variance trade-off. So when the tuning parameter lambda is very small, the bias of the model is also small. But at the same time, the variance can be very large. And when the lambda grows, the model becomes less flexible. And this means that the variance goes down at the same time where the bias goes up. And you can see it from the picture that the variance starts dropping actually quite quickly, but the squared bias grows in much slower speed. So the minimum mean squared error is attained for some intermediate lambda. And in practice, you can use, for example, cross-validation to estimate the optimal value of lambda.